So we'll do one more example of finding the inverse of a function. It's going to be problem number 58. And it's got a little bit of a trick to it, so it's not a bad idea to review it. In 58, f of x is 4x minus 2 over 3x plus 1. So there was like 4 steps in trying to find the inverse of a function. The first one was simple. It's just replace f of x by y. But does anyone remember the second step? What do you do next?
Swap y for x.
Good. Switch x and y. So wherever there's a y, write an x. Where there was an x, write a y. So the second step is going to look like this. I'll have x equals 4y minus 2 over 3y plus 1. So now somehow or another I have to figure out how to get y by itself, which looks like a daunting task. But in any equation where we have rational expressions we're trying to solve, I'll typically recommend that you get rid of the denominators. And in this case, we can do that by multiplying both sides by 3y plus 1. So multiplying by the LCD. So I'll get 3y plus 1 times x equals 4y minus 2 over 3y plus 1 times 3y plus 1. The nice thing is that on the right-hand side, we're going to get some good cancellation. So that disappears. On the left-hand side, let me distribute the x. I'll get 3xy plus x equals 4y minus 2. Well, it doesn't necessarily look a whole lot better, but it is. So what can we do next? Well, let's try and get all the y terms on one side. So to do that, let's see. Let's pick the right-hand side. So I'm going to subtract 3xy from both sides. That'll put the y terms over here. And I want to get rid of everything else, put it on the left-hand side. So I'll add 2 to both sides. Let's see what I get there. Well, on the right-hand side, I get 4y minus 3xy. On the left-hand side, I'll just have x plus 2. Well, it's a little better. At least I have the y's on one side. But now here comes a trick that I showed you with problem number 56 the other day. What do I have to do to help get y by itself? Exactly. We're going to factor out that y. So y times 4 minus 3x equals x plus 2. Almost done with that one. To finish solving for y, thank you. Divide by 4 minus 3x. So x plus 2 over 4 minus 3x equals y. And the final step is to replace y by f inverse of x. So, yay. There's your inverse function. Are you okay with the steps that we did to find f inverse there? Okay. Let's take a look at the graph. Do you remember what I said about the graph of a function and its inverse? Perfect. They're mirror images around the line y equals x. So here we go. Y equals 4x minus 2. And I want to divide that by x, 3x plus 1. 3x plus 1.
This is just a website, right?
This is just a website. Yeah, you can use this for free. You don't even have to create an account. I've got an account that I've created, but that's only because I want to store certain graphs. But yeah, it's free. It's Desmos. Here's something that's kind of even cooler, and it's something you cannot do with your graphing calculator, and that is you can just interchange x and y, x, and then put a y here and a y here, and there you go. So now the two graphs. There's your two graphs. They're mirror images of each other. It's kind of hard to see. Let me put in the line y equals x for ourselves. but it's strange. I mean, you're just getting basically a shift in the graphs, but they are mirror images of each other around that line y equals x. So let's look at a different one. No, I guess one thing I want to point out about this, so our function is the red graph, its inverse is the blue graph. Let me shut off one of these. How do I know this is a function, this red graph? Passes the vertical line test. Does the inverse pass the vertical line test? Let me get rid of this. Does the inverse pass the vertical line test? Yes. They both pass the vertical line test. So it's nice when your function and the inverse pass the vertical line test. That's not always going to happen. Let's take a look at, let's see, problem number, where is it? 62. Problem 62 is going to ask us to look at graph of y equals x squared plus x. Now there's a little bit more to it than that, but let me just write this down for the moment. X squared plus x plus x. There we go. And got to turn that graph on. There we go. So there's our graph. It's a nice parabola, a good function. But what's going to happen when I try and find the inverse? Well, without necessarily finding the inverse, I should letting Desmos do the inverse work for us. Let me put in a y here and a y here. What can you tell me about the inverse? It doesn't pass the vertical line test. Now, there's going to be a way that we can tell that before we do all our work. Before we do the work of trying to find the inverse or anything else, even dealing with the graph, we could tell just by looking at this this function that it would not pass, or that its inverse would not pass the vertical line test. But before we do that, let's actually take care of the problem as it stands in problem number, what was it, 68? 62. All right, so 62. And really they put a little restriction here, that x has to be greater than or equal to negative 1/2. So it's kind of like the restrictions that you had with your piecewise functions. So, okay, x has to be greater than or equal to 1/2. Let's see, and in a similar way, then I can make the following restriction on the inverse. Let's see, 1/2 squared plus 1/2, or negative 1/2. Y has to be greater than negative 1/4. I think that's the right restriction. There we go. So now when we look at this function, kind of the restricted function, and its inverse, does its inverse pass the vertical line test? Yes. So what we're building to is something that's on your handout from the other day. And if you don't have your handout, that's fine. I've got some extras up here. But this is the section 2.8 handout. And it's the horizontal line test. So if any horizontal line intersects your graph at most once, then your graph passes what's called the horizontal line test. If it passes the horizontal line test, then your function is a one-to-one function. Now the nice thing about having a one-to-one function is that the inverse of a one-to-one function also passes the vertical line test. So let's see what that's all about. Let's look back here at our function. And let me just kind of retype this. We'll shut this graph off. If we look again at y equals x squared plus x, does this graph look like it passes the horizontal line test? If you drew a horizontal line through this, say like y equals 3, is that going to intersect the graph at most once? Yeah, it looks like it intersects twice to me. So this would fail the horizontal line test. And what that means, what that tells me without even calculating things, is that the inverse is going to fail the vertical line test. So if I do x equals y squared plus y, and we've seen this graph before, we know that this graph is going to fail the vertical line test, and it does. So it's nice if you have a one-to-one function because your graphs and your inverses are going to be functions. Let's play around with this a little bit more. Let's see. Let's try problem number 86, 88, and 90. Try and decide if these are one-to-one functions, and if not, maybe we can kind of fix that a little bit. So I think I'm going to handle that up here. Let me delete these. The first one, problem number 86, is y equals x minus 1 squared. Is this a one-to-one function? No. It would fail the horizontal line test. Pretty much any horizontal line bigger than y equals 0 is going to intersect the graph at least or exactly twice. So it fails the horizontal line test. But is there a way I can make a restriction on this graph somehow so that it would pass the horizontal line test? Yeah, I can do one of two things. I can do x is greater than or equal to 1 or x is less than or equal to 1. But either way, if I make a restriction here, say x is greater than or equal to 1, now I have something that passes the horizontal line test. So for problem number 86, if I make that restriction, so I've got g of x equals x minus 1 squared. If I restrict that to x greater than or equal to 1 or x less than or equal to 1, then this is a function that will pass the horizontal line test. Now, if it passes the horizontal line test, then it's called a one-to-one function. So g of x equals x minus 1 squared for x greater than or equal to 1 is a one-to-one function. Now what I want you to do for the next one, a similar one, is make a similar restriction so that you have something that passes the horizontal line test for problem number 88. And let's see how we can do with just thinking about problem number 88. Here we've got g of x is the absolute value of x minus 3. What's the graph of the absolute value look like? It's a V, right? Now, how would this differ from that graph? Good, it's been shifted to the right by 3. So, might be helpful to actually take a look at this one. So, let me get rid of that and do y equals the absolute value of x minus 3. So, there's your graph. See if you can't come up with a restriction on this graph so that it would pass the horizontal line test and actually be a one-to-one function. x greater than or equal to 3. Good. So if we make that restriction, and if you were trying to do this on Desmos, all you need to do is put in this curly brace, x greater than or equal to, symbols down here, greater than or equal to 3. So that kind of restricts your domain. And now you have a function that actually passes the horizontal line test, and its inverse would pass the vertical line test. So, nice. Let's write that down here on our sheet. So, x greater than or equal to 3, and that is a one-to-one function. What's another possibility? If I didn't want to do x is greater than or equal to 3, what else could I have done? Yeah. X less than or equal to 3. We're going to make restrictions on x. Yeah. I mean, you could achieve equivalent stuff with restrictions on y, but we're just going to make our restrictions based on x. Okay. So for the next one, if you want to borrow yourself a ruler, that's fine. I've got plenty up here.
The y restriction couldn't work with that one though, could it?
Y is, yeah. You know, I think you're much better off with y with an x restriction, because if you try to restrict things based on y, yeah, I mean, what would you say? Y is greater than or equal to 0, but I think it's probably easier to just make a restriction based on x. Yeah. Yeah, we'll stick with that. Let's take a look at the next one, though. Problem number 90. And I'm going to do my best to copy the graph from the book. Like I said, if you want to borrow a ruler, come on up. So you've got kind of this stick function in the first quadrant. So something here, and then similarly along the x-axis. Okay, so let's put a point on the graph at 0, 1, another point at 4 and 6, 4, 2, 4, 6. So another point at 4 and 6, and a final point at 8 and 8. So that'd be up here. And our function, well, I guess we haven't determined it's a function yet, but it is. Our function just looks like this. It's going to connect the dots between these two. Now this is going to reflect something that I want you to know regarding functions and their inverses, and that is their mirror image nature of those two things. So we have points here at 0, 1, at 4 and 6, and at 8 and 8. What if I ask you to draw the inverse? So this is a graph of y equals f of x. How would you draw the inverse? Well, it is going to be some kind of a mirror image around the line y equals x. So it's going to be through this line. Well, what exactly would you draw? Well, the easiest thing to do is to think of what we do when we find the inverse function. You replace f of x by y, and then what's the second step? It's a crucial step in finding the inverse of a function. After you replace f of x by y, interchange x and y. So we're going to interchange x and y here. Instead of 0, 1, what should I write? 1, 0. So that's here. Instead of 4, 6, I'm going to write 6 and 4. And 8 and 8 stays the same, right? In fact, any point on that line is going to stay the same. So here's my inverse. Nice. And allowing a little bit of slack for my not being as precise as, say, Desmos would be, you know, they look pretty good. They look like they're mirror images of each other around this line. So that's certainly one of the things that I want you to have is this idea about the relationship between the graph of a function and its inverse. There's one more property about the inverse function that I want you to be acquainted with. And we can kind of think of it this way. It's sometimes an alternative way that I use to introduce the subject of inverse functions. And that is, in the Metro Detroit area, there's an interesting relationship between mile roads and addresses. So, mile road and address. Now this only works for your major north-south roads, but on a lot of your major north-south roads like Telegraph, Southfield, DeQuinder, Mound, etc., if you take the mile road times 2,000 and then add 5,000, you get the street address. So for instance, at the corner of Woodward and 11 Mile, there's a gas station there, a gas station and car wash. So if you're at 11 Mile, then there's this nice function, call it f of x equals 2,000x plus 5,000. So 2,000 times 11 plus 5,000 gives you 27,000. And that's the address right there at the corner. Now it works for stuff in between too. If you had, like, you know, Catalpa's 11.5 mile road, okay, so put in 11.5 here and you get 28,000, etc.
What about, isn't there 4 corners? Does it work for all of them?
Well, I mean, I'm not exactly the post office, but you know, on the east side you're gonna have the even numbers, and on the west side you're gonna have odd numbers or something like that. So yeah, maybe across the street is 27,001 or something like that. All right, but it's a pretty good guide. Now, it's not really what you might find useful. Of course, I mean, everyone has Google Maps and stuff like that on their phone nowadays, so this is not as cool as it used to be. But it used to be a nice trick to be able to take an address and figure out, all right, well, if I know the address, then what was the mile road? So I had somebody tell me, oh, come visit my bike store at Hellybuck Cyclery. It's at the 66,000 block of Mound. And I'm like, 66,000? Man, that's way out there. Let's think. That would be like 31 mile road, 30 and a half mile road. It's way out there. And he looked at me in astonishment, like, how'd you know that? I'm like, well, there's an inverse function. So there's an inverse function. What would that be? It would be f inverse of x equals x minus 5,000 divided by 2,000. So that's what goes backwards. The function goes one way, the inverse function goes the other way. So what would happen if I did one then the other? If I did, say, f of 11, and then I did f inverse of that. So let's try and follow it in terms of a picture. In terms of a picture, f of 11 is going to start out here. f of 11 is going to give me 27,000. And then when I do the inverse, 27,000 minus 5,000 divided by 2,000, where am I going to end up? Back at 11. So the function, then the inverse, cancel each other out. And that's the important idea to understand about the inverse function, is that what one does, the other one undoes. They do opposite of each other. So that if you, in general, if you did one then the other, you're going to get back to where you started from. That's one of the conclusions on your handout the other day. If these are inverse functions, f of g of x equals x, and g of f of x equals x. That's an important understanding to have regarding inverse functions. And it's something that they quiz you on with respect to problems like 38 and 40, which we're doing next. So what's 38 and 40? Well, you can almost see these things visually. They give you two functions, and they ask you to check that conclusion that I just showed up on the board. F of x is 3x, and g of x is x over 3. You can kind of see that these are inverse functions. What one does, the other one's going to undo. If you multiply by 3, how would you undo that? You divide by 3. If you divide by 3, how would you undo that? You multiply by 3. So what they're asking you to do is to verify that f of g of x equals x. Well, f of g of x is really f of x over 3 and when I put that in here, that's really going to be 3 times x over 3, and I get back to where I started. So those two functions, when you do one then the other, cancel each other out. What if I did it in the other direction? Well, let's find out. This time it'd be g of 3x. Where am I going to put the 3x? Over 3. It goes into your function for g. So 3x over 3, again, gives you x. So you see these two things canceling each other out. Let's try for a little bit more interesting of a function. Before I move on to that, any thoughts on 38? We okay with that one? It's a good little warm-up example, I hope. Let's try problem number 40. F of x is 2 minus 5x. G of x is 2 minus x over 5. So those are my two functions. What I need to verify is that f of g of x gives me x, and g of f of x gives me x. Yeah, always start from inside out. Good question. So for this first one, and I copied these down, right? Yes? Yeah, I did. So for the first one, starting from the inside out, g of x is 2 minus x over 5. That doesn't look too good. So here we go. 2 minus x over 5. Well, let's go to the rule for f now. The rule for f says take 2 minus 5 times whatever you put in here. So 2 minus 5 times x. In this case, instead of an x, I've got this whole big expression. 2 minus x over 5. Is there any cancellation or simplification I can do here? 5's cancel. Good. So that leaves me with 2 minus x. And if you distribute that carefully, 2 minus 2 plus x simplifies down to x.
Is it defeating the purpose of this exercise to just take one, inverse it, and see if you get the other?
Yes, but that's not a bad. I mean, it's not a bad way to show that one's the inverse of another, is just to calculate it. But yeah, I think it'd be defeating the purpose of it. You know, I'm not sure exactly how I'd ask a question on a test like this. One possibility would be I could say, this is true. What's your conclusion about f and g as functions? What does this tell you? I could ask you to show this, or I just could give you these functions and show one is the inverse of another. And at that point, you'd have your choice. You could either calculate the inverse based on one of these functions, get the other, or you could show this. So in this particular case, it might be easier to just do the calculation. Katie?
What happens to the x when you plug in 2 minus 5? Like you plug in the x.
So we've got f of g of x. G of x is what we're putting into the function f. So x is being replaced by g of x. G of x itself got replaced by 2 minus x over 5 because that's the definition for g. And then I plug that into my function or my rule for f. And there's my rule for f. So I just replaced that x by this whole thing. All right, so we're going to do the same thing the other direction. G of f of x. So again, work from the inside out. That's going to be g of 2x or 2 minus 5x. And plug that into the rule for g. So let me zoom out a little bit. There's your rule for g. Plug 2 minus 5x into the rule for g. So this should simplify much like the other one did. If I distribute the negative in the numerator, I'll get 2 minus 2 plus 5x over 5. The 2 and the minus 2 cancel each other out, so I get 5x over 5. And then again, simplifies down to x, which is exactly what it should do. How are we looking on those last two? 38, 40? Good? All right, thank you. Let me give you some homework. I gave some the other day. This is the complete set of homework for section 2.8. For homework, let's see. Try 7 through 25. What else? 29 through 33. 37 through 43. 49 through 55, I think, is what I assigned the other day. 61, 71, 73, and 85 through 89. I actually think it sounds like an awful lot because I'm throwing out so many problems. Probably sounds a lot worse than it is. Keep in mind these are just the odds. So overall, you're getting less than about 25% of what's available there in terms of homework problems. So I really do try and keep it to a minimum.